Hi, and welcome back. This is the first of two lectures on Chapter 11. And Chapter 11 primarily deals with angular momentum, which is a pretty big important concept, which we'll actually be covering in our second video. Um, the first part of the chapter, though, doesn't deal with angular momentum, but it deals with rolling motion. And we've actually discussed rolling motion before. Um, can't exactly remember which chapter it was in. I believe it was the beginning of rotational motion. But so really, the first part of the chapter is almost like an addendum to the previous chapter, and it just sort of expands on it. But it's a pretty big deal. Um, so what I'm going to do is to discuss a problem that we've actually worked before. And we actually had a lab on it. If you remember does A is equal to uh, G times sine of theta lab. So what I'd like to do is to revisit that particular problem and then talk about how objects roll. Okay. So that said, here's our sort of ubiquitous, mass sitting up an incline. And what I want to do is to find the acceleration for this thing. So we're going to find the acceleration down the incline. Now, we know that, if you draw the forces here, of which you have a normal force, you have a normal force due to the fact that, you have gravity, trying to pull this thing down to the ground like that. And then, let me just go ahead and label these things normal force and the force due to gravity. And, you do what we always do when we have inclined plane problems, and that's you rotate it. So rotate it so that the plane here, acts like the x-axis. So now this would be x, and, this would be y. I guess our poorly drawn normal force vector would actually point up like this. There we go. It's a little bit better, I guess. Kind of. We'll go with that. Anyway, so, we know how to solve this problem. This is an easy problem to solve. We've done problems like this a gajillion times before. So, you draw a force diagram. As we know, the act of rotating our inclined plane makes G point down at an angle like that. We have our normal force here, which now points strictly along the y-axis. If we label our axes like this. So here's our force due to gravity. And, we know now also that the angle here is theta. And we can tell that it's this part right here of the weight, if you will, that causes this thing to accelerate in the x direction. So, if you were to sum up the forces, as we have done many times, you would have a normal force plus the weight, which is going to act on our mass to cause it to experience acceleration. So, in the x direction, we have one force, and that's the weight, at least the x part of it, which we'll call Fgx, and it points in the positive direction. And that's going to act again on the mass to cause it to experience acceleration in the x direction. And in the y-axis, we have a normal force that points up. We have the y part, or the weight, that points down. And those are going to balance each other out. So really, this is what we know we want to look at when it comes to figuring out what this acceleration is going to be. And if you were to take and to break up our weight into components, of which we are intimately familiar with doing now, because we've done it so many times. I guess actually this is theta. I'm not sure why I put that theta there, other than the fact that it is late and I am sleep deprived. So theta, weight, Fgx is really what we're looking for. And as we can see, that's the sine part. So here Fgx, is equal to Fg times sine of theta. And, putting that in here, Fg is m times g. You have the sine of theta. This is, the x part, and that's equal to m times a sub x. The masses cancel, and as you can see, the acceleration for this is just g times sine of theta. Now, look, we have not talked about the shape of this. We haven't talked about how it interacts with the inclined plane as it goes down. And that's because when we first saw this problem, we didn't have the foundation to do that. Now, when you add the ability to roll and you add internal structure into things, that changes this. So, what I'd like to do is to explore that. And part of exploring that is to remind you of another problem that we've worked before. So, if you remember way back when we were talking about friction, which I guess would have been somewhere around, chapter 6, I'd worked a problem where you had a car exit off of an interstate onto an on ramp. Okay, so this right here serves to remind us that when cars make those exits, the exits are typically shaped off of sections of circles, like that. And let's connect this here, there. And so, if you have your car making the exit like this, we know as they round around this that they're experiencing an acceleration towards the center, which we named as centripetal acceleration. And we know the force that's responsible for this inwards acceleration is the static friction between the car's wheel and the ground. So if you think of a wheel, okay, and here's the ground. If you were to look at this point right here, where the wheel is in contact with the ground, that point relative to the ground does not move. If you were to take a snapshot of this wheel in time, that is the point that the wheel sort of trips over, which allows it to roll. It trips over it because it is stuck to the ground at this point at this instant in time because of the static friction. So this sticking, if you want to think of it like that, between the wheel and the ground is what allows the wheel to roll and cause the car to go forward. The sideways action of it, as you go around here, we know that this car's inertia wants to throw it outwards. The sideways action is what keeps the car on the road. So if you were to think of the wheel now sort of facing you like this, and the car going around a turn, and this is the direction, we'll say, of the centripetal acceleration. Once again, if you look at the point of contact between the wheel and the ground, it's this point right here that's just like this. It's rolling on this point, and the wheel is sort of tripping over this point to roll. Okay? Now, I want to remind you something about friction, specifically the static friction. This isn't true about kinetic friction. But remember, the equation for static friction looks like this. Mu sub s times the normal force. But when you calculate this, regardless of how quickly this car goes around the circle, you get the same number. Remember, static friction, the value that you get when you do this, is an upper limit. It says that if my frictional force actually exceeds this, then the car slides and you go into kinetic friction mode. Okay? So remember, the equals really here is better as an inequality. It could be less than or equal to or greater than equal to, depending upon what you're looking for. Now, so with that having been said, let's add some actual detail to our rolling problem, okay, or our thing sliding down, or better yet, rolling down an incline. Now, we worked an example back in the previous chapter when we talked about kinetic energy, and I showed you that the velocity at the bottom for different shapes was different due to the fact that as these things roll without slipping, that rolling action soaks up different amounts of the actual potential energy that they start off with. But what I want to explore now is the act of rolling. Okay, so here's a shape. I don't know. Well, what do we want this to be? One will let it be a sphere. Okay. Now, as this thing rolls, okay, it is going to have a moment of inertia. That's going to be the moment of inertia of the sphere, which is 2/5 mr squared. Okay. So let's not forget that. I'm going to write that over here. The moment of inertia of a sphere is 2/5 mr squared. So our sphere as it rolls obviously is going to have a radius. Here's the center point right here. Okay. So here's our radius. We'll let this thing start off from rest. It really doesn't matter because our goal is to find, we want to find the acceleration. Okay. So that said, let's talk about the forces that are acting on this. Now, if it's rolling without slipping, what that means is at this point of contact right here, that again is an anchor. So this thing, it wants to slide down this way. Okay, it wants to slide without rolling, which means that at this point right here, you have a frictional force back this way that's preventing this thing from sliding down and instead is making it trip. So here's your static frictional force this way. Okay. Now acting through the center of mass, because remember it's the center of mass of this thing that traces out the parabola if you were to fire it through the air. Acting through the center of mass, you have its weight. Now at the point of contact here too, we have a normal force due to the fact that its weight's pressing there. Okay, you got a normal force. So if I were to just simply look at a force diagram for this thing, and what I'm going to do is to play the same game as we did previously. It's an inclined plane problem. So what do? You rotate it, right? So let's take this thing right here. I'm going to move it over here. Wow, that's interesting. Didn't want to go. So let me fix that issue. Must have not got the top. Okay, there we go. We'll bring this over here. I'm going to rotate it like that. I guess I rotated my I sub s as well, huh? I'll just redo that. Okay, so what's happening is this thing is going to experience acceleration, taking it down the incline. And the acceleration, like I said, is in reference to where its center of mass is, which for a uniform sphere is dead in the center. Now, that said, though, as this thing rotates, the point of contact right here is continually sort of changing as it rotates, right? So there's actually an acceleration here. And this would be the tangential acceleration. In this case, the acceleration is in the same direction as f sub s. Okay, at this point, it would be up. At this point, it would be this way. So you have, a tangential acceleration here, a sub t. That's back this way, at least, at this location, in the same direction as the static frictional force. Now, this acceleration, though, because it's at an anchored point, is also the same as the acceleration as this thing feels going down. If you go back and you review my discussion about rotational motion some time ago, you'll see we talked about that. There's also tangential velocity and all that stuff, which we really don't need to work this problem. Now, that said, having put it in this particular mode now, if you will, we have a static frictional force back this way. Okay, we have a normal force that goes up like this. And we also have the weight, which goes down like this. Now, I didn't label the angle over here, but I'll go ahead and do it. We're just going to call it theta, just like we did before. And here's theta. Okay? So you got your normal force, you got your weight, and you also have your static frictional force this way. Okay? Now, the condition for this thing to roll without slipping is that our static frictional force, whatever it is, it needs to be less than or equal to mu sub s times n. Now, again, why is that? Well, remember, over here, when we had discussed this, this is an inequality. If it's equal to, this tells you the maximum amount of static friction that it can resist with. And for this thing to roll without slipping, we do not want whatever this is to exceed that. Because if it does, then it's going to slide. We're not in a static mode, we're in a kinetic mode, and the kinetic mode is a little bit more complicated to deal with. Okay? So, that said, we have our three forces here that are acting on this thing to make it want to roll down the incline. And let me just sum up our forces. So we sum the forces up to get the net force, of which we have 3. We have a normal force, we have our static frictional force, and plus we have our weight right there. And that's going to act on our mass m to cause it to experience acceleration. So I guess I should probably label it as a mass m2. Now, so in the x direction, what we have is this. We have a negative static frictional force, and we have a positive x component of the weight, and that's going to act on our mass to cause it to experience acceleration in the x direction. In the y direction, it's same old. We have a normal force pointing up, and we also have the y part of gravity pointing down, and those are going to balance each other out because this thing isn't hopping or doing anything funny as it goes down. Now, let's go ahead and, again, break up our gravitational force into components. Here's Fg. Here's Fgx. Here's Fgy. So Fgx, as written, is the sine part. That's Fg times sine of theta, or mg sine of theta. Fgy is the y part, which would be, again, mg cosine of theta, as drawn. Okay? So that said, what I'm going to do is I'm going to plug this in, but I don't want to touch the form of F sub s. Remember, this is our condition right here. We want for this thing to roll without slipping as it goes down. It must be true that whatever frictional force that it needs to supply is going to be less than or equal to the maximum that it can give. Okay, that's the condition. So that said, let's just go ahead and work here. For the x part, I have minus F sub s. Like I said, I don't want to touch the form of that right now. Plus Fgx. Fgx is mg times sine of theta. And that's going to act on our mass to cause it to experience acceleration in the x direction. Likewise, our normal force here, minus the Fgy, which is mg cosine theta, is equal to 0. All right. So let's just sort of bracket these things and remember them. And now let me show you how you actually integrate in the fact that you have a shape that's rolling. So to do that, we're going to draw our next diagram, which is a torque diagram, and I'll draw it right here. So here we have two forces that are acting through the center of our object. Now, let me remind you about torque. Torque, remember, depends upon a force being applied a distance from a point of rotation. So the point of rotation for the sphere is the dead center. Okay. So if I were to apply, for example, a force acting right through the center, R would be 0, which means that when I look at torque, which is R cross F, the distance that this force would be 0 from the center, and that would produce 0 torque, because no force through the center is going to make this thing rotate. Likewise, let's pretend that I applied my force straight down through R through the center, like, for example, the normal force here. That, if you go back and you look at my examples of torque and stuff, that doesn't give you any torque. So out of these three forces that we have here, only one of them actually is going to produce any torque whatsoever, and that's the frictional force. Okay, So what we have here is relative to the center. So this thing is being drawn at the center of mass. Relative to the center, you have a force being applied r away, like this, at the point of contact. And the nice thing about the way this works is that this angle here is by definition 90 degrees. Okay? So this is r vector. This is F sub s right there. Now, so there's only one torque here. I'm going to call this tau 1. Okay? It is r times F sub s in magnitude. And if you were to use the right-hand rule, it would place it into the screen. Okay? So into the screen, let's see, r cross F into the screen. Into the screen here is clockwise rotation. And clockwise rotation we know is negative. So you could represent this as a vector by saying that it's in, or by putting a minus sign out in front, which is good enough. Okay, since torque, at least as we deal with it, is strictly sort of a one-dimensional concept. Now, so that said, when you sum up your torque here, which I'll do right here, when you sum up all of your torques to get the net torque, you only have one torque here, and that's tau sub 1. And what that's going to do is to act on the inertial mass of our sphere and cause it to experience angular acceleration. Okay? So, if you think along one direction, which, like I said, rotational motion for the most part is just 1D motion with the changes of variables, then you have, since this is in a negative direction, minus r F sub s, which is what our torque is. And what that's going to do is to act on our mass to cause it to experience acceleration. But I'm going to put in the direction of the acceleration there, because at the end of the day, we really only care about the magnitude of this. So if I remember alpha, our angular acceleration, is a magnitude, then I can do this. So what this means is we have a third equation here, which I'll write over here, and that's that r F sub s, the torque here, acts on the inertial mass of this thing and causes it to accelerate. Now, this is angular acceleration. And like I said, the a here, which would be the acceleration in the x direction, is in magnitude the same as our tangential acceleration. Now, a tangential in magnitude, like I said, is the same as ax. It can be written as r times alpha, which means that we can rewrite alpha as a sub x over r. Okay? So if I take this and I look at that, r F sub s is equal to I times a sub x over r. Now, this right here is going to allow us to actually look and see what our frictional force looks like. So F sub s is due to this thing rotating and not slipping as it goes down. If I solve for F sub s, it's a sub x over r squared, because I move this over here and it goes into the bottom. So now I have a form of this frictional force right here, which means that I can rewrite this the following way. Minus I a sub x over r squared plus mg sine of theta is equal to m times a sub x. Now, I want to plug in the fact that this thing is a sphere, and its moment of inertia is 2/5 mr squared. So if I were to put that in here, 2/5 mr squared times a sub x over r squared plus mg sine of theta is equal to m times a sub x. Now look, the m's cancel. I also see over here an r squared in the bottom and an r squared in the top. Those go away too. So what I have here at the end of the day is minus 2/5 a sub x plus g sine of theta is equal to a sub x. So if I were to move this over to the right-hand side and solve for a sub x, let me move it over there to begin with. If I pull the a sub x out here on the right-hand side, two fifths plus one. One is 5/5. This would be 7/5. If I solve for a sub x, I get that a sub x is equal to 5/7 g sine of theta. Now look, this is what you get for, like I said, a sphere. If you roll the hoop down here, you're going to get a different acceleration. If you roll a wheel down, you're going to get a different acceleration. It's all because of this, the behavior of the moment of inertia. Okay, but if you compare this to what we had over here, where we don't take into account the actual shape of this thing as it goes down, then as you can see, things are different. Okay, so here, taking into account structure, you end up with this. All right. Now, so that said, this is our acceleration. We can also ask the question, if we're worrying about this condition right here, if we want to know, for example, what would be the maximum angle, for example, that we could take and elevate this thing to, that would cause it to slide. We can look at this and we can answer it. So our condition that we need to satisfy is that F sub s is less than or equal to mu sub s times the normal force. Now the normal force we get from this. Normal force is just equal to mg times cosine of theta. So F sub s here needs to be less than or equal to mu sub s times mg cosine of theta. And we also have, like I said, a mathematical form for what the frictional force looks like, due to the fact that this thing is rolling, without slipping. Okay, so on the left-hand side, we have I times a sub x over r squared. And look, we've already found out what a sub x is this right here. Okay, now I, we know, comes from over here, from the shape of this sphere. It's 2/5 mr squared. So this right here, like I said, is 2/5 mr squared. So that would be 2/5 mr squared times a sub x over r squared. This needs to be less than or equal to mu sub s mg cosine of theta. Okay, so again, the r's go away. You've got a mass on the left-hand side and the right-hand side. They cancel. And I have a 2/5 a sub x is less than or equal to mu sub s times g times cosine of theta. But look, like I said, we have a sub x here. So that would be 2/5 times 5/7 g sine of theta needs to be less than or equal to mu sub s g cosine of theta. So again, if I look here, the 5's cancel. Okay, the g's go away. So 2/7 sine of theta needs to be less than or equal to mu sub s times cosine of theta. Now, if I take and move the 2/7 to the right-hand side and then divide both sides through by cosine, I have sine of theta over cosine of theta is less than or equal to 7/2 mu sub s. Well, sine of theta over cosine of theta is tangent. So if I set this to be an equals, what that means is that my angle needs to be, if I do an arc tangent here, of 7/2 mu sub s, my angle here needs to be less than or equal to this for this thing to roll without slipping. Okay, now let's compare that to a situation like this, to where we have a frictional force. Okay, if you have a frictional force here, and we've done this problem before, okay, like for example, you have a static frictional force and you're asking the question, now, what is the maximum angle that I can elevate this thing to before it starts to slide? Okay, now if you work that same problem, not taking into account, like I said, internal structure, and you sum up your forces now, of which you have 3, just like the other problem, except we have torque there as well. You have normal force, you have your static frictional force, you have weight. Okay, now we're going to set these equal to 0. It's actually inequality, like I said. If you look at what happens in the x direction, you have your negative static frictional force. This is going to be, let's see, plus FGX is equal to 0. In y, we have a normal force, again, minus FGY is equal to 0. Okay, if you put in the form of FGX and FGY, noting the fact that the y part is a cosine, then what you have is minus F sub s plus FGX, which is mg sine of theta, is equal to 0. Again, the normal force we know is going to be mg cosine of theta. And now we can plug in the form of F sub s minus mu sub s times the normal force. The normal force is mg cosine of theta, rather. Excuse me. Plus mg sine of theta. You got all these cancellations that happen. And then when you actually solve for what the angle is, what you end up with is that you need to take the tangent, or the arctangent rather, of mu sub s. So without adding structure, this is what you get. This is your maximum angle. But when you add structure to it, as you can see, you have this factor of 7/2 out in front. Okay, so this is going to change the angle substantially. And again, for different shapes, you're going to get different accelerations, and you're also going to have different frictional forces. So the end result of all this is that if you want something to roll without slipping, the act of rolling is actually a pretty complicated thing. Okay. You could work the same problem and ask the question, okay, what if it slips, but the slipping, is due to, some sort of coefficient of kinetic friction that's present. You can work the same problem, but what you're going to discover is in a situation like that, your tangential acceleration and your actual acceleration aren't going to be the same, because it's going to be rolling at a different rate than how it moves. Okay, now, so this is it for our discussion about rolling without slipping. Like I said, this is probably better thought of as an addendum to the previous chapter, expanding on that. And what we're going to talk about in our next video is angular momentum, and I'll see you then.